Recent announcements about solid-state batteries from Volkswagen, Toyota, and NIO have once again reignited optimism across the global electric vehicle market. A handful of confident lines in a press release is often enough to send stock prices soaring. Those announcements push headlines toward phrases like, "the next battery revolution." For financial markets, that narrative is intoxicating. For engineers, it sounds uncomfortably familiar. Those who witnessed lithium-ion batteries evolve from fragile laboratory curiosities into reliable automotive systems tend to ask a different question. The real issue is not whether solid-state batteries have theoretical potential. The real issue is whether they can survive the brutal realities of mass automotive production. History suggests that promise alone is never enough. Bob Gallion, former Chief Technology Officer of CATL and now head of Gallion Energy, has little patience for inflated expectations. Solid-state batteries, he argues, are genuinely promising technologies, but their path to commercialization will not be fundamentally different from lithium-ion. Lithium-ion did not arrive fully formed. It required decades of incremental improvement. That maturation process involved painful lessons. Safety failures occurred. Thermal runaway incidents happened. Cycle life was limited. Manufacturing stability was poor. Costs had to fall. Production yields had to rise. Reliability had to become boring. There is no technical or economic reason to believe solid-state batteries can bypass this long and unforgiving phase. This explains why, despite excitement surrounding announcements from Volkswagen, QuantumScape, Toyota, and NIO, many battery experts interviewed by IEEE Spectrum remain cautious. The pattern is strikingly consistent. Performance metrics look impressive on paper. They are often achieved under idealized laboratory conditions. Publicly available data demonstrating durability under real-world automotive stress remains scarce. The gap between prototype and production is where most battery technologies fail. Elon Musk famously referred to this phase as manufacturing hell. Solid-state batteries are no exception. Mechanical stress exposes weaknesses. Environmental variation reveals flaws. Manufacturing inconsistency amplifies failure rates. Controlled laboratory tests cannot reveal these problems. Until these challenges are solved, claims of breakthroughs remain incomplete. At the center of the issue lies validation. Solid-state batteries are not new inventions. They did not appear suddenly in recent years. Variants have existed for decades. They have been used primarily in niche applications. These include medical implants. They include sensors. They include specialty electronics. In these environments, cost is secondary. Operating conditions are tightly controlled. Electric vehicles operate in a completely different reality. Automotive batteries must withstand constant vibration. They must survive sudden mechanical shocks. They must tolerate wide temperature swings. They must endure dense charge-discharge cycles over many years. Manufacturers must validate performance. They must validate durability. They must validate cost. All three must succeed simultaneously. If any one pillar fails, the entire value proposition collapses. On paper, the appeal of solid-state batteries is undeniable. Replacing liquid electrolytes with solid materials offers higher thermal stability. These materials are typically ceramics or glass. Intrinsic safety is theoretically improved. Higher energy density is also theoretically achievable. This is especially true when paired with lithium metal anodes. These characteristics explain why automakers continue to invest. In theory, a solid electrolyte could enable faster charging. Thermal runaway could be avoided. Higher energy density could reduce battery size. Battery weight could decrease. Vehicle efficiency could improve. Together, these benefits suggest electric vehicles with longer range. They suggest shorter charging times. They suggest lower fire risk. But theory alone does not build cars. Volkswagen, through its battery subsidiary PowerCo SE, has leaned heavily into this narrative. The company recently announced test results for lithium metal cells supplied by QuantumScape. The announcement claimed 1,000 charge cycles with 95% capacity retention. Volkswagen translated this into a headline-friendly claim. That claim suggested more than 500,000 kilometers of driving without significant degradation. From a marketing perspective, the message is compelling. From an engineering perspective, it raises immediate questions. What were the test conditions? What stack pressure was applied? How were temperature gradients managed? These details matter far more than headline numbers. Engineers immediately ask what happens outside the laboratory. How do these cells behave under constant vibration on rough roads? What is the failure rate when millions of cells are produced? Manufacturing variation is inevitable. How does a solid electrolyte respond to microcracking? What happens under repeated mechanical stress over time? These are not abstract concerns. They are daily realities of automotive engineering. They rarely appear in early-stage test data. Cycle counts alone cannot answer them. Gallian illustrates the problem with a simple example. Imagine a vehicle traveling at highway speed hitting a deep pothole. How does a solid electrolyte respond to that sudden mechanical shock? A solid electrolyte is far more brittle than a liquid. Does it fracture internally? Does it lose interfacial contact with the electrodes? These failure modes are extremely difficult to simulate fully in laboratories. They are even harder to eliminate at scale. No spreadsheet can resolve that uncertainty. No press release can either. Toyota has announced plans to integrate solid-state batteries into production vehicles starting in 2027. The company has publicly targeted a range of around 1,000 kilometers. It has also targeted the ability to charge to 80% in 10 minutes. NIO has attracted attention with its so-called semi-solid-state battery. The pack is rated at 150 kilowatt-hours. However, the details reveal important distinctions. According to Sam Abuelsamid of Guidehouse Insights, NIO's battery is essentially a conventional NMC lithium-ion cell. It uses a gel electrolyte. This lithium polymer approach has existed for more than 10 years. While the term semi-solid is not technically incorrect, it lacks the defining characteristics of a true solid-state electrolyte. This distinction is not merely semantic. Semi-solid batteries can still be punctured. They tend to fail in ways similar to traditional lithium-ion cells during a crash. True solid-state batteries behave differently. They are more likely to fracture. These fundamentally different failure mechanisms imply very different safety challenges. They also imply different design trade-offs. It is worth remembering that similar gel-based batteries were already used in production vehicles. One example is the 2009 Hyundai Sonata Hybrid. Gallian summarizes these challenges using what he calls the 5 golden rules of batteries: safety, performance, lifespan, cost, environmental impact.